Good evening, everyone, and welcome to your favorite sleep channel, The Droning Professor. Tonight, we're going to learn about how gravity warps time. So as you make yourselves comfortable, please take a moment to let us know where you're listening from and feel free to subscribe. Now, as always, take a moment for some deep breaths, letting your mind and body relax for a good night of sleep. Tonight's lesson might be the strangest hour and a half of your academic life, where we're going to talk about how gravity, that thing that makes you spill coffee on yourself when you trip, is actually bending time itself like a pretzel. Yes, time. The thing you never have enough of before an exam. Turns out, it's not just moving forward uniformly for everyone. It's getting stretched and squeezed by massive objects, and by the end of this lesson, you'll understand why astronauts age slightly slower than the rest of us, which honestly seems unfair given they already get to go to space. Let's start with a question that should bother you. What is time? No, seriously, what is it? You check it on your phone, you complain there's not enough of it, you say it flies when you're having fun, but what actually is it? The ancient Greeks thought time was just change, the movement from one state to another. Aristotle, who had opinions about literally everything, said time was the counting of motion. If nothing moved, there'd be no time. Isaac Newton, centuries later, disagreed completely. Newton thought time was absolute. It flowed uniformly throughout the universe, ticking away like a cosmic metronome that nothing could affect. 1 second on Earth was 1 second on Jupiter was 1 second in the farthest galaxy. Time, in Newton's view, was the ultimate constant, the one thing we could all agree on, no matter where we were or how fast we were moving. Newton wrote in his Principia Mathematica that absolute, true, and mathematical time flows equably without relation to anything external. That's fancy. 1700s speak, for time doesn't care what you think or what you're doing, it just keeps going. And honestly, Newton's view makes sense, right? It matches our everyday experience. When you and your friend both time how long it takes to microwave popcorn, you get the same answer. Time seems universal. Newton's laws worked beautifully for everything from falling apples to planetary orbits. The universe seemed to run like clockwork, predictable and orderly, with time as the unchanging backdrop. This worked so well for so long that by the 1800s, physicists were getting a little cocky. Lord Kelvin supposedly said in 1890 that there was nothing new to be discovered in physics, just more precise measurements. Spoiler alert, he was catastrophically wrong. The late 1800s and early 1900s were about to blow physics wide open, and time was going to be one of the first casualties. The first crack in Newton's perfect clockwork universe came from thinking about light. Light is weird. It's a wave, but a wave of what? Ocean waves move through water, sound waves move through air, but what does light move through? Physicists in the 1800s proposed something called the luminiferous aether, which sounds like something from a fantasy novel, but was actually a serious scientific hypothesis. The aether was supposed to be this invisible substance that filled all of space, and light waves rippled through it like waves on a pond. Made sense, except for one tiny problem. Nobody could find it. In 1887, two physicists named Albert Michelson and Edward Morley did an experiment that should have detected Earth's motion through this ether. Think about it. If light needs a medium to travel through, and Earth is zooming through space at about 30 kilometers per second, then we should be able to detect a kind of cosmic headwind. When you stick your hand out of a moving car, you feel the wind, right? Same principle. They built this incredibly precise device using mirrors and split beams of light and measured whether light traveled at different speeds depending on Earth's direction through the ether. The result? Nothing. No difference. No aether wind. Light traveled at the same speed in every direction, regardless of Earth's motion. This was deeply, profoundly weird. The physics community kind of panicked. Some people proposed that maybe Earth was dragging the ether along with it, like you drag water when you swim. Others suggested that objects physically contract when moving through the aether in just the right way to hide the effect. It was a mess of ad hoc explanations trying to save Newton's worldview. Then along came a patent clerk in Switzerland who had too much time to think during his day job. His name was Albert Einstein, and in 1905, at the age of 26, he published a paper that casually destroyed everything we thought we knew about space and time. The paper was called On the Electrodynamics of Moving Bodies, which is possibly the most boring title for one of the most revolutionary papers in physics history. We now call the ideas in that paper special relativity. Einstein started with two simple postulates. First, the laws of physics are the same in all inertial reference frames. That means if you're sitting still or moving at a constant velocity, physics works the same way. You can't do an experiment inside a smoothly moving train that tells you whether you're moving or stopped, which you've probably experienced if you've ever been sitting in a parked train and the train next to you starts moving, and for a second you can't tell who's actually moving. Second postulate, and this is the killer. The speed of light in a vacuum is constant for all observers, regardless of their motion or the motion of the light source. Always the same. Roughly 299,792,458 meters per second, which we usually round to 3 times 10 to the 8th power meters per second for convenience. Let's call it c for short. Einstein said c is the same, whether you're standing still, running toward the light source, or flying away from it in a rocket ship. This seems impossible based on our everyday experience. If I throw a ball forward from a moving car, its speed relative to the ground is the car's speed plus my throwing speed. But light doesn't work that way. Light always measures c, no matter what. Now, if the speed of light is always constant, and speed equals distance divided by time, then for this to work, either distance or time or both have to be flexible. And that's exactly what Einstein realized. Space and time aren't fixed backdrops. They're dynamic. They bend and stretch depending on your motion. This leads to all sorts of bizarre consequences. Time dilation is one of them. If you and I are moving relative to each other, we'll measure time differently. Specifically, moving clocks run slow. Not because there's something wrong with the clock, but because time itself is passing slower for the moving observer from the perspective of someone watching them. This isn't a small effect at everyday speeds. At highway speeds, you'd have to drive for billions of years to lose even a second. But at speeds close to the speed of light, it becomes dramatic. Here's the classic thought experiment. Imagine you're on a spaceship with a light clock, which is just a photon of light bouncing between two mirrors, and each round trip counts as one tick. You're moving past me at, let's say, 87% of the speed of light. From your perspective on the spaceship, the light just goes straight up and down, tick-tock, everything normal. But from my perspective, watching you zoom by, that photon has to travel a diagonal path because you're moving. The light has to cover more distance to complete one tick. But light always travels at speed c. So if it's covering more distance at the same speed, it must take more time. Your clock, from my perspective, is running slow. You're aging slower than me. If you fly around in that spaceship for what feels like 1 year to you and then come back, I might have aged 2 years, or 10 years, or 1,000 years, depending on how fast you were going. This has been tested over and over again. We've flown atomic clocks on airplanes and compared them to clocks on the ground, and sure enough, the flying clocks lose a tiny bit of time, exactly as relativity predicts. Astronauts on the International Space Station age slower than people on Earth by a few milliseconds per year because they're moving fast in orbit. It's not much, but it's real, and it's measurable. The mathematical relationship is given by the Lorentz factor, which we write as gamma equals 1 divided by the square root of 1 minus v squared divided by c squared. Here v is your velocity and c is the speed of light. When you're moving slowly compared to light, v is much smaller than c, so v squared over c squared is basically 0, and gamma is essentially 1. Time flows normally, but as you approach the speed of light, v gets close to c, that v squared over c squared term approaches 1, you're dividing by the square root of something approaching 0, and gamma shoots toward infinity. Time dilation becomes extreme. At 99.999% of the speed of light, gamma is about 224. 1 year for you would be 224 years for someone watching you. At the speed of light itself, gamma would be infinite, which is one reason nothing with mass can actually reach the speed of light. It would require infinite energy, and time would essentially stop. Photons, which have no mass and travel at light speed, don't experience time at all. From a photon's perspective, if it had one, it's emitted and absorbed in the same instant, even if it's traveled across the entire universe. Now, special relativity is called special because it only applies to special cases. Constant velocities, no acceleration, no gravity. It's relativity light. Einstein spent the next 10 years working on what happens when you include acceleration and gravity, and the result was general relativity, published in 1915. This is where things get really wild, and where gravity finally enters our story about time. In special relativity, space and time are woven together into something called space-time, a four-dimensional fabric where 3 dimensions are space and 1 is time. General relativity says that mass and energy curve this space-time fabric. Gravity isn't a force pulling on you, at least not in the traditional sense. Gravity is the curvature of space-time itself. Massive objects like planets and stars create dips and curves in space-time, and when you move through curved space-time, you follow what are called geodesics, the straightest possible paths through the curve. To you, it feels like you're being pulled by a force, but really you're just following the natural contours of curved space-time. John Wheeler, a physicist who had a gift for memorable phrases, summarized general relativity like this: space-time tells matter how to move, matter tells space-time how to curve. It's a feedback loop. Mass curves space-time, and that curvature affects how things move, including light and time itself. Let me give you an analogy that everyone uses because it actually works. Imagine space-time as a stretched rubber sheet. Put a bowling ball, representing a massive object like the sun, in the middle. The sheet sags around the bowling ball, creating a dip. Now roll a marble, representing a planet, near the bowling ball. The marble doesn't travel in a straight line. It curves around the bowling ball, following the contour of the dip. From far away, it looks like the bowling ball is pulling the marble toward it, but really the marble is just following the curved surface. That's how gravity works in general relativity. Earth orbits the sun not because the sun is pulling it with some mysterious action at a distance force, but because the sun's mass curves space-time and Earth is following that curve. Now, this analogy has limits. Real space-time is four-dimensional, not two-dimensional like a sheet, and the curvature happens in time as well as space. But it gives you the right mental picture. Here's where it gets relevant to our discussion. If mass curves space-time, it curves time itself. Time runs slower in stronger gravitational fields. This is called gravitational time dilation. The closer you are to a massive object, the slower your clock ticks relative to someone farther away. This isn't because your clock is broken. Time itself is literally passing slower. Einstein's field equations, which are the mathematical heart of general relativity, describe exactly how mass and energy curve space-time. The equations are fiendishly complicated. They're actually a set of 10 interrelated partial differential equations that even Einstein struggled to solve. The full tensor equation is written as r subscript mu nu minus 1/2 times r times g subscript mu nu plus lambda times g subscript mu nu equals 8 pi. G divided by c to the 4th power times t subscript mu nu. If that sounds like alphabet soup, don't worry. Even physicists use computers to solve these equations in all but the simplest cases. What matters for us is what they predict. Time flows slower in stronger gravitational fields. Let's make this concrete. GPS satellites. You use them every time you check Google Maps or ask your phone for directions. Those satellites orbit about 20,000 kilometers above Earth's surface, where Earth's gravitational field is weaker than at the surface. According to general relativity, clocks on those satellites should run faster than clocks on the ground because they're in a weaker gravitational field. How much faster? About 45 microseconds per day. That doesn't sound like much, but GPS works by timing how long radio signals take to travel from satellites to your phone. Radio waves travel at the speed of light, so 45 microseconds translates to about 14 kilometers of error. If we didn't account for gravitational time dilation, your GPS would tell you you're in the wrong city within hours and would be completely useless within days. The engineers who built GPS had to program Einstein's equations into the satellites to correct for this effect. Every time you successfully navigate to a coffee shop, you're relying on general relativity. Think about that next time you're annoyed your GPS recalculated your route. But wait, there's more, because special relativity also affects GPS satellites. Remember, moving clocks run slow, and satellites are moving fast, about 14,000 kilometers per hour relative to the ground. This causes their clocks to run slower by about 7 microseconds per day. So you've got two competing effects. General relativity making the clocks run faster by 45 microseconds per day. Special relativity making them run slower by 7 microseconds per day. The net effect is they run faster by about 38 microseconds per day. This has to be corrected constantly. GPS is proof that relativity isn't just abstract theoretical physics. It's real, it matters, and it affects your daily life. Let's push this further. What happens near really massive objects? The sun curves space-time more than Earth does, because it's much more massive. Time runs about 66 microseconds per year slower on the sun's surface compared to Earth, assuming you could somehow stand on the sun's surface without being vaporized. Not a huge effect, but what about something much more massive and compact? A neutron star, which is a dead star crushed down to about 20 kilometers across but with the mass of our entire sun. Near a neutron star's surface, time runs dramatically slower. Or even more extreme, a black hole. Black holes are regions of space-time where the curvature becomes so extreme that not even light can escape. The boundary of no return around a black hole is called the event horizon. At the event horizon of a non-rotating black hole, which we call a Schwarzschild black hole, time dilation becomes infinite from the perspective of a distant observer. If you watched someone fall into a black hole, from your safe distance, you'd see them slow down as they approached the event horizon. They'd move slower and slower, their watch ticking slower and slower, and they'd appear to freeze right at the horizon, taking infinite time to actually cross it. Meanwhile, from the perspective of the person falling in, everything feels normal. Their watch ticks normally, they cross the horizon in finite time, and then they get spaghettified by tidal forces, which is the technical term for being stretched like taffy, because the gravity at your feet is much stronger than at your head. But to you watching from far away, they never quite cross. They just get dimmer and redder and appear to freeze. This has profound implications. The inside of a black hole is effectively cut off from the outside universe, not just spatially but temporally. Events inside the horizon happen from a distant perspective in the infinite future. They're beyond the time-like boundary of the observable universe. This has led to all sorts of mind-bending questions about what happens to information that falls into a black hole, which was the subject of a famous bet between Stephen Hawking and Kip Thorne, but we're getting off track. The point is, near black holes, time gets seriously weird. In 2014, there was a movie called Interstellar that actually did a pretty good job visualizing this. The characters visit a planet orbiting close to a supermassive black hole called Gargantua, and 1 hour on the planet's surface equals 7 years back on their spaceship because of extreme gravitational time dilation. When they returned to the ship after what felt like a few hours, their colleague who stayed behind has aged decades. The physics consultants for that movie, including Kip Thorne, actually worked out the math to make sure it was plausible. It's Hollywood, so they took some liberties, but the basic principle is sound. Strong gravity equals slow time. Now let's talk about the equivalence principle, because it's crucial to understanding why gravity affects time. The equivalence principle is the insight that launched general relativity, and Einstein called it the happiest thought of his life, which tells you something about how physicists find joy. Here's the idea. Imagine you're in an elevator in space, far from any planets or stars, floating weightless. Now someone starts accelerating the elevator upward at 9.8 meters per second squared, the same acceleration as Earth's gravity. You'd be pressed to the floor, you'd feel weight. If you dropped a ball, it would fall to the floor. In fact, from inside the elevator, there's no experiment you could do to tell whether you're in space being accelerated or sitting stationary on Earth's surface. The two situations are equivalent. Acceleration and gravity produce identical effects locally. This was Einstein's great insight. Gravity and acceleration are two sides of the same coin. They're equivalent. Now here's where it gets interesting for time. Imagine you're in that accelerating elevator in space, and you shine a light from the back wall toward the front wall. From your perspective in the elevator, the light beam has to cross the elevator while the elevator is accelerating forward. By the time the light reaches the front wall has moved, and it looks to you like the light beam curved downward. It bent. Now, if acceleration curves light, and acceleration is equivalent to gravity, then gravity must also curve light. This was one of the first predictions of general relativity that could be tested. In 1919, Arthur Eddington led an expedition to observe a solar eclipse and measured the positions of stars near the sunday. During the eclipse, the sun's glare was blocked, so stars near the sun's edge became visible. Eddington found that starlight passing close to the sun was indeed bent by the sun's gravity, exactly as Einstein predicted. This made Einstein an international celebrity overnight. The headlines in the London Times said, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Einstein became synonymous with genius. But light bending is just part of the story. If light curves in a gravitational field, and light is electromagnetic radiation oscillating at a particular frequency, what happens to that frequency in a gravitational field? This is where time dilation comes in. Imagine a photon climbing out of a gravitational well, like light escaping from the surface of a massive planet. As it climbs, it's moving against gravity, so it loses energy. For light, energy is related to frequency by Planck's equation. Energy equals Planck's constant times frequency. If the photon loses energy, its frequency decreases. Lower frequency means redder light, so we call this gravitational redshift. But here's another way to think about it. If time runs slower deep in a gravitational well, then an oscillating electromagnetic wave down there oscillates slower from the perspective of someone higher up. Slower oscillation means lower frequency means redder light. Gravitational time dilation and gravitational redshift are two ways of describing the same phenomenon. This has been measured. In 1960, two physicists named Robert Pound and Glenn Rebka measured gravitational redshift using gamma rays traveling up and down a tower at Harvard. The tower was only about 22 meters tall, so the effect was incredibly tiny, but with very precise equipment, they detected it. The frequency of gamma rays at the top of the tower was slightly lower than at the bottom, exactly as general relativity predicted. Here's a fun thought experiment called the twin paradox, which ties together special and general relativity. You have two twins, Alice and Bob. Alice stays on Earth. Bob gets in a rocket and flies to a nearby star at high speed, then turns around and comes back. When Bob returns, he's younger than Alice. From Alice's perspective, this makes sense because Bob was moving fast, so his clock ran slow. But from Bob's perspective, Alice was the one moving, so shouldn't Alice be younger? This seems like a contradiction. The resolution is that the situation isn't symmetric. Bob had to accelerate to leave Earth, decelerate at the star, accelerate back, and decelerate again on Earth. He experienced forces. Alice didn't. During Bob's acceleration phases, he's technically in a non-inertial reference frame, and general relativity applies. The acceleration breaks the symmetry. When you work through the math carefully, accounting for the acceleration, everyone agrees. Bob is younger. This isn't just theoretical. We've tested it with atomic clocks on airplanes. Clocks flown around the world, which experienced both velocity-related time dilation from special relativity and gravitational time dilation from altitude changes, showed exactly the predicted time difference when compared to clocks left on the ground. The universe doesn't care about your intuition. It does what the equations say. Let's think bigger. What about the universe as a whole? General relativity doesn't just describe how individual masses curve space-time. It describes the evolution of the entire universe. In 1922, Alexander Friedman used Einstein's field equations to show that the universe couldn't be static. It had to be either expanding or contracting. Einstein initially hated this idea. He was so convinced the universe should be static that he added a term to his equations called the cosmological constant, represented by lambda, to force a static solution. He later called this his biggest blunder, although interestingly, the cosmological constant has made a comeback in modern physics as dark energy. In 1929, Edwin Hubble observed that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. The universe is expanding. If you run the expansion backward, you get to a point where everything was compressed into an incredibly hot, dense state. This is the Big Bang, which happened about 13.8 billion years ago. Now, here's the weird part. The Big Bang wasn't an explosion in space. It was an expansion of space itself. Space between galaxies is literally stretching, carrying galaxies apart. And if space is expanding, then the geometry of space-time is evolving over time. In an expanding universe, time itself has a cosmological aspect. There's a cosmic time, a notion of simultaneity defined by the expansion. Observers at rest relative to the cosmic expansion, often called co-moving observers, can agree on what now means on cosmological scales. This seems to contradict special relativity, where simultaneity is relative, but remember, general relativity is the more complete theory. The universe has a particular structure, a particular way space-time is curved by the overall distribution of matter and energy, and that gives rise to a preferred reference frame. But this is only on the largest scales. Locally, special relativity still applies. If you and I are moving relative to each other, we still disagree on simultaneity. The universe's expansion is only noticeable over vast distances. Over the distance between Earth and the Sun, or even between the Sun and the nearest star, space isn't expanding significantly. Gravity holds solar systems and galaxies together. It's only on scales of hundreds of millions of light years that expansion dominates. Here's something that will blow your mind. In an expanding universe, there are parts of the universe we can never observe, not because the light hasn't had time to reach us yet, but because the expansion is carrying them away faster than light can travel through expanding space. This doesn't violate special relativity, which says nothing can move through space faster than light. Space itself can expand as fast as it wants. The observable universe has a boundary, about 46 billion light-years away in all directions, and beyond that boundary are galaxies we'll never see, events that have already happened that we'll never observe, because the light will never reach us. Those regions are causally disconnected from us, not just spatially but temporally. We can never know what time it is there in any meaningful sense. Let's bring this back down to Earth with another practical example: gravitational waves. In 1916, shortly after publishing General Relativity, Einstein realized the theory predicted something bizarre. Just like accelerating electric charges produce electromagnetic waves, accelerating masses should produce gravitational waves, ripples in space-time itself. These waves would travel at the speed of light, stretching and squeezing space-time as they passed. Einstein thought they'd be far too weak to ever detect. For decades, they were purely theoretical. Then in the 1970s and 80s, physicists built massive detectors called interferometers. The most famous are the two LIGO detectors, one in Louisiana and one in Washington state. Each detector is an L-shaped tunnel with 4-kilometer-long arms. A laser beam is split and sent down both arms, bounces off mirrors at the ends, and comes back. If space-time is stretched or squeezed by a passing gravitational wave, one arm gets slightly longer while the other gets slightly shorter, and the laser beams go out of sync. The sensitivity required is insane. LIGO can detect a change in arm length smaller than 1,000th the diameter of a proton. On September 14, 2015, LIGO detected gravitational waves for the first time, created by two black holes spiraling into each other and merging 1.3 billion years ago. The waves traveled for 1.3 billion years through expanding space and jiggled LIGO's mirrors by about 10 to the negative 18 meters. When I say space-time is dynamic, this is what I mean. Space-time literally vibrates when massive objects accelerate. And as these waves pass through you, they alternately stretch and squeeze your body, though by amounts far too small to notice or measure without incredibly sophisticated equipment. Time dilation oscillates as the wave passes. Clocks would speed up and slow down rhythmically, though again, by unmeasurably tiny amounts for any gravitational wave we could detect. Since that first detection, LIGO and other detectors have observed dozens of gravitational wave events from merging black holes, merging neutron stars, and other violent cosmic events. We're now doing astronomy with space-time itself. One of the weirdest implications of general relativity is that time had a beginning. If the universe is expanding and you run the expansion backward, you get to a singularity, a point where density and temperature become infinite and space-time curvature becomes infinite. The Big Bang. But what does it mean for time to have a beginning? Before the Big Bang, there was no before. Time itself didn't exist. The question what happened before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because you've reached the boundary of the thing you're asking about. This is philosophically disturbing. Our brains are wired to think in terms of cause and effect, but cause and effect require time. If time had a beginning, what caused that beginning? We don't know. Quantum mechanics and general relativity might provide some answers when we figure out how to combine them properly into a theory of quantum gravity. But that's still an open problem in physics. Stephen Hawking and James Hartle proposed a model where the universe has no boundary in imaginary time, which is a mathematical trick involving complex numbers. But the honest answer is, we don't fully understand what happened at the very beginning, or even if beginning is the right word. Time also might have an end, depending on the ultimate fate of the universe. If the universe's expansion is accelerating, which observations suggested is due to dark energy, then the universe will expand forever, getting colder and more dilute. Stars will burn out, black holes will evaporate through Hawking radiation, and eventually, after something like 10 to the 100 years, the universe will reach heat death, a state of maximum entropy where no organized structures remain and nothing interesting can happen. Time would still technically exist, but nothing would change. In a sense, time would become meaningless. Alternatively, if dark energy behaves differently than we think, the universe might eventually stop expanding and recollapse in a big crunch, the opposite of the Big Bang. Time would end in a singularity, just as it began in one. Or maybe quantum gravity effects prevent singularities, and something else happens. We don't know. The far future of the universe and time itself is still speculative. Here's something that might help make sense of this. Time isn't really a thing. It's a dimension of space-time, a parameter that describes change. Asking what time is made of or where it comes from is like asking what north is made of. It's a direction, a way of organizing information about the universe. Einstein himself said, "The distinction between past, present, and future is only a stubbornly persistent illusion." What he meant is that, in the block universe view of relativity, all of space-time exists as a four-dimensional structure. The past and future are just as real as the present. Your entire life, from birth to death, is laid out as a world line through space-time. The sensation of time flowing, of moving from past to future, might be an artifact of consciousness, of how we process memories and experiences. This is the eternalism view, and it's deeply weird. It suggests that in some sense, dinosaurs still exist in the past, and whatever you'll be doing tomorrow already exists in the future. You don't move through time. Your consciousness experiences different slices of space-time sequentially. Now, not all physicists agree with this interpretation. Some prefer presentism, where only the present is real, but presentism is hard to square with relativity because relativity says simultaneity is relative. My now is not your now if we're moving relative to each other. Whose present is the real present? Eternalism avoids this problem by saying it's all equally real. Let's talk about something really fun, time travel. You've been waiting for this. Admit it. General relativity doesn't forbid time travel. In fact, it allows for some truly bizarre space-time geometries where closed time-like curves exist, paths through space-time that loop back on themselves, so you could travel into your own past. The famous Gödel metric, found by Kurt Gödel in 1949, describes a rotating universe where such curves exist. If the universe rotates as a whole, you could take a path through space-time that brings you back to the same spatial location at an earlier time. The catch is, our universe doesn't rotate as a whole, so the Gödel metric doesn't apply to reality, but other solutions exist. The Kerr metric describes a rotating black hole, and it contains regions where closed time-like curves might be possible, though getting to them would require traveling through the black hole's event horizon and probably getting destroyed by tidal forces or other instabilities. In 1988, Kip Thorne and his colleagues showed that traversable wormholes, shortcuts through space-time connecting two distant points, could potentially allow time travel if you manipulated them correctly. You'd need exotic matter with negative energy density to keep the wormhole open, and we're not sure such matter can exist in sufficient quantities, but it's not ruled out by known physics. So, time travel might be possible, in principle, but we have no idea how to actually do it, and there are serious problems. The biggest problem is causality. If you can travel back in time, you could kill your own grandfather before your parent was born, erasing your own existence, which creates a paradox. How can you exist to go back and kill your grandfather if you were never born? There are various proposed solutions. Maybe paradoxes are prevented by physical laws we don't understand yet. Maybe the universe splits into parallel timelines whenever a time traveler changes something, so you kill your grandfather in an alternate timeline, not your own. Maybe attempts to create time machines fail due to quantum effects, or maybe time travel is simply forbidden by some yet unknown principle, a chronology protection conjecture as Stephen Hawking called it. The universe seems to conspire to prevent paradoxes, but we don't have proof. It's an open question. What we do know is that traveling forward in time is easy. Just move fast or hang out near a black hole, and you'll jump into the future relative to people far away. Backward time travel is the tricky part, and probably impossible, though we can't be certain. Quantum mechanics adds another wrinkle to our understanding of time. In quantum mechanics, particles exist in superpositions of states until measured. Schrödinger's cat is in a superposition of alive and dead until you open the box. This is usually discussed in terms of space, where the particle is here and there simultaneously, but it also applies to time in some interpretations. There's a thing called the quantum Zeno effect where frequent measurements can freeze a quantum system in its initial state, effectively stopping its evolution. Time still passes, but the system doesn't change. It's as if watching the pot prevents it from boiling, except this is a real effect, not just a saying. Conversely, under the right conditions, you can get the quantum anti-Zeno effect, where frequent measurements speed up decay. Quantum mechanics and general relativity don't play nicely together, and reconciling them is one of the biggest unsolved problems in physics. At the Planck scale, about 10 to the negative 35 meters and 10 to the negative 43 seconds, both quantum effects and space-time curvature become important, and our current theories break down. We need a theory of quantum gravity, something like string theory or loop quantum gravity, to describe what happens at those scales. At the Planck scale, space-time itself might become grainy or foamy, fluctuating wildly, and time might not even be continuous. It might come in discrete chunks, quantum ticks of some cosmic clock. We don't know. It's an active area of research. Here's a thought that should keep you up at night. If time is affected by gravity, and different observers measure time differently depending on their motion and position in a gravitational field, is there any objective truth about time? When did something really happen? The answer general relativity gives is that space-time events have definite locations in the four-dimensional space-time manifold. Two observers might disagree on when something happened or how long it lasted, but they'll agree on the space-time interval between events, a quantity that combines spatial and temporal separation in a way that's the same for all observers. The space-time interval is like the distance between 2 points, but in 4 dimensions instead of 3, and with a minus sign in front of the time part. It's given by delta s squared equals minus c squared times delta t squared plus delta x squared plus delta y squared plus delta z squared. Different observers slice up spacetime into space and time differently, but they all agree on delta s squared. That's the invariant, the objective thing. So, in a sense, there is an objective reality in relativity, but it's not the three-dimensional space and one-dimensional time we're used to. It's four-dimensional space-time as a unified whole. Time and space are intertwined, two aspects of the same thing, and you can't fully understand one without the other. Let me give you one more example of gravitational time dilation that's almost poetic. Massive stars end their lives in supernova explosions, and sometimes what's left behind is a neutron star or a black hole. When a star collapses, the surface is falling inward at tremendous speeds, and the gravitational field becomes incredibly strong. From the perspective of someone watching from far away, the collapse appears to slow down as the surface approaches what will become the event horizon. The star appears to freeze, getting dimmer and redder as photons struggle to escape the intense gravity. The collapse takes infinite time from an outside perspective, even though the star itself experiences the collapse in finite time, probably just a fraction of a second. The dying star is reaching toward us from the past, its light stretched by gravity, its final moments extended across eternity from our point of view. Every black hole in the universe is, in a sense, a frozen moment of stellar death, visible to us as a darkened ember that never quite finishes collapsing. It's beautiful and eerie and completely contrary to our everyday experience, but it's what the equations predict and what we observe. I want to address something that confuses a lot of people. When we say time slows down in strong gravity, we don't mean you subjectively feel time passing slowly. If you're deep in a gravitational well, everything seems normal to you. Your heartbeat, your thoughts, your watch, all tick along at their usual pace from your perspective. It's only when you compare your clock to someone else's clock far from the gravitational source that you see the difference. This is what we mean by relativity. There's no absolute time, no universal clock. Time is relative to the observer. This can lead to situations where two events that are simultaneous for one observer happen at different times for another observer. Simultaneity is not absolute. This seems to violate common sense, but common sense evolved to deal with walking speeds and everyday gravity. not near light speeds and black holes. The universe doesn't care about our intuitions. It operates according to mathematical laws that sometimes produce results that seem absurd until you get used to them. Here's a practical question you might wonder about. If gravity slows time and Earth has gravity, do people living at different elevations age at different rates? Yes. People living at sea level age slightly slower than people living on mountains because they're deeper in Earth's gravitational well. The effect is tiny. At the top of Mount Everest, about 9,000 meters above sea level, you'd gain about 90 microseconds per year compared to someone at sea level, meaning you'd age faster by that amount. Over a lifetime of 80 years, that's about 7 milliseconds. You'd barely be younger than your twin who lived at the beach. But it's measurable with precise enough atomic clocks, and it's been measured. In 2010, researchers at NIST demonstrated optical clocks precise enough to measure gravitational time dilation over a height difference of just 33 centimeters, 1 foot. They could literally show that a clock on a table ticked faster than a clock on the floor. Think about that. Your head ages faster than your feet, by an utterly negligible amount, but it's real. Every time you climb a ladder, you've moved into a region where time flows slightly faster. Of course, if you climb quickly, the velocity-related time dilation from special relativity might counteract this. You'd have to do the calculation to see which effect wins. This ties into something called gravitational potential. The gravitational potential at a point in space is related to how much work you'd have to do to move an object there from infinity. At Earth's surface, the gravitational potential is negative. At higher altitudes, it's less negative, approaching zero at infinite distance. Time dilation is related to this potential. The more negative the potential, the deeper in the gravitational well you are, the slower time runs. The time dilation factor for weak fields like Earth's is approximately 1 plus phi divided by c squared, where phi is the gravitational potential. For Earth's surface, phi is about negative 6.3 times 10 to the 7th meters squared per second squared, and c squared is 9 times 10 to the 16th, so the ratio is tiny, about 7 times 10 to the negative 10. That's why we don't notice gravitational time dilation in daily life. But for strong fields like near-neutron stars or black holes, the effect becomes significant. Let's talk about frame dragging, another prediction of general relativity. A rotating massive object doesn't just curve spacetime, it drags spacetime around with it like a spinning ball in Honey Drags the Honey. This is called the Lenz-Thirring effect, predicted in 1918. Near a rotating black hole or neutron star, spacetime itself is swirling, and anything nearby is dragged along. You couldn't stay stationary relative to distant stars even if you tried. You'd be forced to orbit in the same direction as the rotation. This affects time as well. The structure of spacetime near a rotating object is different from a non-rotating one, and time flows differently depending on your position and motion. In 2004, NASA's Gravity Probe B satellite measured frame dragging around Earth. Earth's rotation is slow, and the effect is tiny, but it's there, exactly as predicted. The probe carried incredibly sensitive gyroscopes, and over the course of a year, their spin axes were shifted by frame dragging by about 37 thousandths of an arcsecond, roughly the width of a human hair seen from 10 miles away. But it was measurable, and it matched the theory. Black holes come in different types. A Schwarzschild black hole is non-rotating and uncharged, the simplest kind. A Kerr black hole is rotating. A Reissner-Nordstrom black hole is charged but non-rotating. A Kerr-Newman black hole is both rotating and charged. Each has different space-time geometry and different implications for time dilation. Rotating black holes are particularly interesting because they have an ergosphere, a region outside the event horizon where spacetime is dragged around so strongly that you can't stay still. You must orbit. But you can still escape from the ergosphere, unlike from inside the event horizon. In principle, you could extract energy from a rotating black hole by dropping something into the ergosphere and catching it on the way out. a process called the Penrose process. The black hole's rotation slows down slightly, and you get energy. This isn't science fiction. It's allowed by the mathematics of general relativity. Whether it's practical is another question. Let's zoom out to cosmology again. The expansion of the universe affects time in interesting ways. As the universe expands, the wavelength of light traveling through it gets stretched. This is cosmological redshift, different from gravitational redshift, but related. Light from distant galaxies is redshifted because space itself has expanded during the light's journey. The farther away the galaxy, the more the light is redshifted. We quantify this with the redshift parameter z, defined as the change in wavelength divided by the original wavelength. A galaxy with z equals 1 has had its light wavelengths doubled by the expansion. When we observe that galaxy, we're seeing it as it was when the universe was about half its current age. The light has been traveling for billions of years, and during that time, the universe has expanded significantly. But here's the thing. That galaxy is also experiencing time differently than we are in a cosmic sense. Because of the expansion, there's a kind of stretching of time as well as space. Events in distant galaxies appear to us to happen in slow motion because the expansion is stretching the time intervals between photons reaching us. Supernovae in distant galaxies take longer to brighten and fade than nearby ones, not because they're intrinsically different, but because the universe's expansion is stretching the time signal. This has been observed. High redshift supernovae appear to evolve more slowly by exactly the factor predicted by cosmology. The universe itself is dilating time. There's a concept called cosmic time, which is the time measured by a hypothetical observer at rest relative to the cosmic microwave background, the afterglow of the Big Bang. Observers moving relative to the CMB measure time differently, but most galaxies, including ours, are moving relatively slowly compared to the speed of light, so we're all close to comoving observers. The age of the universe, 13.8 billion years, is measured in cosmic time, but this is only an average. Different parts of the universe, if they're moving differently or in different gravitational fields, have experienced different amounts of proper time since the Big Bang. There's no single universal clock that's ticked the same number of times everywhere. Time is local. One of the predictions of general relativity that seems most like science fiction is the existence of white holes. A white hole is the time reversal of a black hole. While a black hole is a region nothing can escape from, a white hole is a region nothing can enter. Matter and light can only leave a white hole. The event horizon works in reverse. From outside, you'd see stuff being ejected from the white hole, possibly violently, but you could never send anything in. White holes are mathematically allowed by the Einstein field equations, but we've never observed one, and there are good reasons to think they can't exist in our universe. They're probably unstable. The slightest perturbation would cause them to collapse or evaporate. But they're fun to think about and show up in some speculative models of cosmology and quantum gravity. Some theories propose that the Big Bang itself was a white hole event, a region where matter and energy erupted into space-time. But this is highly speculative. Let's talk about something more tangible: gravitational lensing. When light from a distant object passes near a massive object on its way to us, the light's path is bent by the massive object's gravity. This is gravitational lensing, and it can create multiple images of the distant object, or smear it into arcs and rings, or magnify it. Einstein predicted this, and it was first observed during the 1919 eclipse expedition. But modern astronomy uses gravitational lensing as a tool. We can use it to map the distribution of dark matter in galaxy clusters, because dark matter has gravity and bends light even though it doesn't emit light. We can also use it to study distant quasars and galaxies that would otherwise be too faint to see. But here's the relevance to time. When light takes different paths around a gravitational lens, the paths have different lengths and pass through regions with different gravitational time dilation. This means light following different paths arrives at different times. If the distant object is variable, like a quasar that flickers, we see the same flicker multiple times, once from each lensed image, with delays between them. The delays can be days, weeks, or months, depending on the geometry and the mass of the lens. By measuring these time delays, we can learn about the distribution of mass in the lens and even measure the expansion rate of the universe. Gravitational lensing gives us a way to literally see time delays caused by gravity. There's an effect called the Shapiro delay, sometimes called gravitational time delay, which is similar. When a radio signal passes close to a massive object like the Sun, it takes longer to reach its destination than you'd expect from just the geometric path length. This is because the signal is passing through curved spacetime, and time runs slower near the sunday. The signal's clock, so to speak, is ticking slower, so it takes longer. This was first measured in the 1960s and 70s, using radar signals bounced off Venus and Mercury when they were on the opposite side of the Sun from Earth. The delay was microseconds, but it matched Einstein's predictions. We now use Shapiro delay measurements to test general relativity in the solar system with exquisite precision. Every test so far confirms the theory. I want to come back to the twin paradox for a moment because there's a subtlety worth mentioning. In the standard twin paradox, one twin travels at high speed and returns younger. But you could also have a twin paradox with gravity. Imagine one twin stays in orbit around Earth, in the International Space Station, while the other stays on the ground. Who ages faster? The twin in orbit is moving faster, so special relativity says their clock should run slower. But the twin in orbit is also farther from Earth's center, in a weaker gravitational field, so general relativity says their clock should run faster. Which effect wins? For the ISS, it turns out the velocity effect is slightly larger, so astronauts on the ISS age slower than people on the ground, but only by a few milliseconds per 6-month mission. If they orbited higher, where the gravitational effect is larger and velocity can be slower, the gravitational effect would dominate and they'd age faster. There's an altitude, about 3,000 kilometers above Earth's surface, where the two effects exactly cancel. At that altitude, clocks tick at the same rate as on the ground, even though they're moving and at a different gravitational potential. This is sometimes called the zero gravitational time dilation altitude. Above it, you age faster than on the ground. Below it, slower. This is all measurable and has been measured. Let's get even weirder. In some solutions to Einstein's equations, you can have closed time-like curves paths through space-time that loop back on themselves. If you followed such a path, you'd end up at an earlier point in your own timeline. This is time travel to the past, and it's allowed by the math. The Gödel universe has them. The interior of a rotating black hole, a Kerr black hole, might have them, though the regions are probably unstable and unreachable. Some wormhole spacetimes have them if you manipulate the wormhole correctly. But here's the problem. If closed time-like curves exist, causality breaks down. You could, in principle, interact with your own past. The grandfather paradox becomes a real concern. Most physicists think there must be some mechanism that prevents closed time-like curves from forming in our universe, or prevents you from traversing them, or resolves paradoxes if you do. Some invoke quantum mechanics, arguing that quantum effects create a kind of back reaction that blows up the space-time geometry and destroys the time machine. Stephen Hawking's chronology protection conjecture says this, but it's not proven. It's an interesting question. Does the universe have built-in protection against time travel, or is it allowed but just incredibly difficult to achieve? We don't know. Here's something practical and weird. Time dilation affects particle physics. Unstable particles have a characteristic half-life, the time it takes for half of a sample to decay. But if those particles are moving fast, their internal clocks run slow due to special relativity, and they live longer from our perspective. Muons, which are heavy cousins of electrons, are created in Earth's upper atmosphere when cosmic rays hit air molecules. Muons have a half-life of about 2 microseconds. At the speed they're created, they should only travel about 600 meters before decaying. But Earth's atmosphere is much thicker than that, tens of kilometers. Yet we detect muons at sea level, far more than we should if their half-life were unchanged. The reason is time dilation. From our perspective, the muons are moving at nearly the speed of light. Their clocks run slow, and they live much longer, allowing them to reach the ground. From the muon's perspective, it's not living longer. Instead, the atmosphere is contracted in the direction of motion due to length contraction, another consequence of relativity, so it doesn't have as far to travel. Either way you look at it, relativity explains why we detect muons. This was one of the early confirmations of special relativity. Every time you see a muon detector in a physics lab, you're seeing proof that time is relative. Particle accelerators, like the Large Hadron Collider at CERN, also rely on relativistic effects. Protons in the LHC are accelerated to 99.9999991% of the speed of light. At that speed, the time dilation factor gamma is about 7,000. From the proton's perspective, if it had one, it's only circling the ring for a fraction of a second before colliding. From our perspective, we keep it circling for hours, millions of times around the 27-kilometer ring, before we collide it with another proton. The proton has tremendous kinetic energy, and when it collides, that energy can be converted into new particles according to Einstein's equation E equals mc squared. Energy equals mass times the speed of light squared. This is another gift from special relativity. Mass and energy are interchangeable. The faster something moves, the more kinetic energy it has, and that energy contributes to its effective mass. At relativistic speeds, it becomes harder and harder to accelerate something further because you're not just accelerating its rest mass, but its growing kinetic energy too. This is why nothing with mass can reach the speed of light. It would take infinite energy. Let's talk about the cosmological constant again because it's relevant to time. In 1998, 2 teams of astronomers studying distant supernovae found something shocking. The universe's expansion is accelerating. Galaxies aren't just moving apart, they're moving apart faster and faster over time. This was completely unexpected. Gravity should slow the expansion, pulling galaxies back together. Something is pushing them apart, and we call that something dark energy. The simplest explanation for dark energy is Einstein's cosmological constant, a form of energy inherent to space itself. The more space there is, the more dark energy there is, driving the expansion. If dark energy is real and its density stays constant while the universe expands, the expansion will accelerate forever. The universe will become increasingly cold and empty, with galaxies beyond our local group receding beyond the horizon of what we can ever observe. This affects time in a cosmic sense. The observable universe will shrink in the far future, not because space is contracting, but because distant regions are accelerating away and their light will never reach us. Future civilizations, trillions of years from now, might look up and see a nearly empty sky, all other galaxies having receded beyond visibility. Their view of the universe would be dramatically different from ours, and they might not even know the universe had a Big Bang or is expanding unless they somehow preserved our knowledge. Time in general relativity is part of the space-time continuum, dynamically interacting with matter and energy. It's not a passive stage where events occur. It's an active participant. Mass curves time. Motion dilates time. Gravity slows time. Expansion stretches time. Time is flexible, malleable, relative. Yet it also has structure. Events have a causal order. You can't affect the past, at least not without closed time-like curves, which probably don't exist. Light cones define what regions of space-time can influence or be influenced by a given event. If two events are space-like separated, far enough apart that light couldn't travel between them, then they can't causally affect each other, and their time order depends on your reference frame. But if they're time-like separated, within each other's light cones, their causal order is absolute. Everyone agrees which happened first. This causal structure is fundamental. Quantum field theory, which combines quantum mechanics and special relativity, treats spacetime as a fixed background and focuses on fields that permeate it. But in general relativity, spacetime is dynamic. Combining quantum mechanics with general relativity has been a challenge for nearly a century. String theory proposes that fundamental particles are tiny vibrating strings, and in this framework, spacetime might emerge from more fundamental principles. Loop quantum gravity proposes that spacetime itself is quantized, made of discrete loops at the Planck scale. Other approaches include causal set theory, where spacetime is a network of causally related events, and emergent gravity theories, where gravity and spacetime aren't fundamental but arise from deeper quantum information principles. We don't know which, if any, of these is correct, but they all suggest that time, at the deepest level, might not be what it seems. It might be emergent, constructed from something more fundamental. This is deeply speculative, but it's where cutting-edge physics is heading. Here's something that bothers people. If time is relative and flexible, what's the now? Is there a universal present moment? In special relativity, the answer is no. Simultaneity depends on your reference frame. What's happening now on a distant star depends on your state of motion. In general relativity, you can define a cosmic time in an expanding universe, but that's only a large-scale average, not a fundamental truth. Locally, now is still relative. Some physicists and philosophers think time is an illusion, that the sensation of flowing time, of a moving present, is a feature of consciousness, not the universe. All moments exist equally in the block universe. Others think the flow of time is real, connected to the arrow of time, the fact that entropy increases and we remember the past but not the future. This is an open question in philosophy of physics. My personal view, for what it's worth, is that time is real as a dimension of space-time, but the flow of time, the sensation that time passes, is something that arises from how we process information and memories. But that's philosophy, not physics. And you shouldn't mistake my opinion for settled science. One last mind-bending topic, the holographic principle. This is the idea that all the information contained in a volume of space can be encoded on the boundary of that region, like a hologram encodes three-dimensional information on a two-dimensional surface. This came out of studying black holes. A black hole's entropy, its information content, is proportional to the area of its event horizon, not its volume. This is bizarre. For normal objects, entropy scales with volume. For black holes, it scales with surface area. This suggests that space might be fundamentally two-dimensional at a quantum level, with the appearance of three dimensions emerging from the way information is organized. If true, space-time and time itself might be holographic projections of something more fundamental. This is highly speculative and controversial, but it's taken seriously in theoretical physics because it might help reconcile quantum mechanics and gravity. Time in a holographic universe would be emergent, not fundamental. Again, we don't know if this is right, but it's a fascinating possibility. We've covered a lot of ground. Time is warped by gravity. It slows near massive objects. It's relative, depending on your motion and position. It had a beginning, might have an end, and isn't the universal constant we intuitively think it is. GPS satellites prove it. Atomic clocks measure it. Black holes stretch it to infinity. The expansion of the universe dilates it across cosmic scales. And at the deepest level, time might not even be fundamental, but emergent from quantum information or holographic principles or something we haven't dreamed of yet. General relativity revolutionized our understanding and gave us a mathematical framework to predict and measure these effects with stunning precision. Every test we've done, From the 1919 eclipse to LIGO's gravitational waves to GPS corrections, confirms that Einstein was right. Gravity warps space-time, and time is part of that warping. What does this mean for you, sitting here listening to this? Probably not much in practical terms. You're not going to notice time dilation walking upstairs. You're not going to age differently than your friends in any noticeable way, unless you become an astronaut or somehow get close to a black hole. But you live in a universe where time is flexible, where the past and future are stitched into the same four-dimensional fabric as space, where causality and the speed of light impose limits on what's possible, where the universe itself is expanding and carrying distant galaxies away from us, where time might have begun with the Big Bang and might end in heat, death, or a big crunch, or something stranger. You live in a universe described by equations so beautiful and precise that they predicted the existence of black holes, gravitational waves, and the bending of starlight decades before we observed them. You live in a universe where a patent clerk in 1905 could figure out the nature of time through pure thought and math, and be proven right again and again for over a century. That's extraordinary. The universe is stranger and more wonderful than our everyday intuitions suggest. Gravity isn't just a force pulling things down. It's the curvature of reality itself, bending not just space but time. And we've figured this out. We've measured it. We've tested it. We've built technologies that rely on it. That should fill you with wonder. We're standing here, on a planet orbiting a star in a galaxy made of billions of stars, in a universe with billions of galaxies, and we've worked out the rules. We understand, at least partially, how time works at the deepest levels we've been able to probe, and there's still more to learn. We don't have quantum gravity yet. We don't fully understand dark energy or dark matter. We don't know if time travel is possible or forbidden. We don't know what happened before the Big Bang, or what will happen in the far future. There are mysteries left, and that's exciting. The story isn't over. So the next time you check your GPS, think about Einstein. The next time you look up at the stars, remember their light has been traveling for years or centuries or billions of years to reach you. And during that journey, the universe has expanded, space has stretched, and time has been dilated by cosmic expansion. The next time someone says they don't have enough time, you can smile and think, well, time is relative. If you really want more time, just move faster or climb a mountain. You'll age slightly faster, not enough to matter, but enough to be real. The universe is weirder than you think, and gravity warps time. Good night. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you.